Greetings and welcome, friends. We are starting a new chapter today. We're talking about transformations. Hooray! And we'll actually end up using some of these transformations to prove our previously assumed true theorems from last chapter, like corresponding angles theorem, which is interesting that so far we haven't proven that to you, but we called it a theorem. It says the following. Here's some vocabulary for you. A vector is a quantity that has both direction and magnitude, or size. Magnitude and size, right? So a vector, you perhaps have seen these if you've taken a physics class. But yeah, it's like the so here. And it's represented in the coordinate plane by an arrow drawn from one point to another. And let's see, the diagram shows a vector. The initial point is the starting point. All right, so the direction of this matters, which makes sense because vectors have direction. And the starting point is P, and the terminal point is Q. The vector is named PQ. And notice this. This is called a harpoon. It is not a ray kind of notation symbol there. It's only got half of the arrow there, and it's a harpoon as though it's out hunting a white whale sort of thing. Yes, perhaps named Moby. So here we go. So this is a vector. You know it's a vector because it's got that subtle notation there. You could read it as vector PQ. Notice vectors. Yes, I could describe a vector based on its angle. Maybe I'll call that theta, a Greek letter theta. And its distance, maybe I'll call that r or something like that, for like a radius almost, you could imagine. But I also could view them in terms of their horizontal and vertical components. So instead of moving whatever this angle is at that distance r, you could also end up at the same location by moving right 5 and up 3. And so the horizontal and vertical components are, right, these two other vectors, actually. You could view the vector PQ as being the sum of this horizontal vector and that vertical vector. But we don't have to talk about vector addition or subtraction in this course, fortunately. But I just want to point out that, the end result is the same overall move from point P to Q. And you can write a vector in component form by using these. Notice these are not parentheses. These are little angled brackets like so. Make sure that it doesn't end up looking like a less than sign or a greater than sign. But no guarantees, Liam, that mine will not. Look. Interesting. So let's see. Let's take a look at this. Example 1. Identifying vector components. In the diagram, name the vector. Let's call this vector, I don't know. Just kidding. And so use a little harpoon notation. And JK, if I want to think about this in terms of its horizontal component, would have been, looks like it's moving over 3. Right, and vertically, its vertical component is going up 4. Right, so I could call vector JK. I could label it as vector 3, 4. Doing the horizontal portion first, and then the vertical in a near x, y order. You could imagine, which is an appropriate way to conceive of this. So let's see. So why are we talking about vectors today? So briefly, because we're talking about transformations. Ooh. Transformation is a function that moves or changes a figure in some way to produce a new figure called an image. Another name for the original figure is called the pre-image. The prefix pre is something your English department could tell you about, perhaps. The points on the pre-image are the inputs for the transformation, and the points on the image are the outputs. And so the first type of transformation we're talking about, because there will be a variety of them, and even a composition of them later on, is called a translation. All right, so transformation, translation. I realize you probably will maybe mix up those things if you remember things by first initial like I do, which is a terrible way to remember things. But it says translations move every point of a figure the same distance and direction. You could say that it maps or moves points P and Q along the vector. Notice that this vector is being applied to all of these points to P prime and Q prime. Also, check this out. If I was to describe vector P prime, that vector, right? What? It looks like this one is moving over A units and up B units. So the vector that is could be used to describe this translation is the vector AB. And notice that to find the new point P prime, right, Ryan? I could just simply add A to the X coordinate and add B to the Y coordinate. Nothing too fancy. Notice some properties come out of this. It says that P prime is equal to Q prime. Those are measurements of those vectors, and so these vectors are congruent to each other in that regard. And also the vectors are parallel. All right, so that makes sense, right? Nothing too crazy there. And then it says, or those two are equal and the vectors are collinear. It's interesting. So it is possible that if the vector was happening to move an object in the same direction as a portion of one of its segments, right? So if I was moving this segment by a vector that happened to be along the same path, all right, that the vectors are collinear. All right, is what would happen. So that's all that's referring to as far as like this case 2 sort of situation. All right, let's try to get this to work here. All right. Fortunately, the application of this is not that difficult. It's just naming conventions for the sake of standard convention right there. So let's see. The vertices of triangle ABC are as follows. Let's graph it. Hey, I conveniently have a pre-made grid here. Thanks, past self. You're welcome, Mr. Waddy. 0, 3. So left, right, 0, move up 3. Here is point A. 2, 4, over 2, up 4. Bravo. And C is over 1, up 0. Charlie. And so there's my original. That's what I was thinking of too. Wow. I didn't know. Oh, but I actually projected my thought into your mind is what I did. That, ooh, Chipotle now. So here's a triangle ABC. If I want to translate it by vector 5, -1. So watch this. So that means A is going to move over 5. Who would have thought? Down 1. Okay? So A prime is right here. Right? Really not that fancy. Oh, man, it just undoodled. Way too much. All right, I'll switch colors again. What do you think, Ryan? What's your friend say? I don't. So anyone that's out there with my name is an imposter. I have one, but I've used it once. Also, I will not friendliest any of you. Yeah. So let's see. For B, right 5, down 1. Here's B prime. And for C, we'll go right 5 and down 1. Here's C prime. And one of the things that is true about transformations, as we'll see in a moment, is that they are said to be rigid, where they create an image from the pre-image that is congruent and is, right, all of its Right, not only are its sides congruent, but all of its angle measures are equal as well. Do I follow no one? What? Wow. 6. Probably from 2.5 years ago? 2015. Right, the only reason I used Instagram there was so I could do the linear blur effect, so that the legal documentation could not be seen. Actually, regarding that, I thank you for reminding me. I have to update the state of Vermont regarding my son's lifetime hunting and fishing license because his name and social security number have changed. Good reminder. Thanks, Instagram. I don't. I hunt for video game deals, and I often buy them and then never play them. And it's sad. It's the worst game to play. Let's see. Write a rule for the translation. Okay. Ooh. Check this out. To move from A to B horizontally, it looks like it went this way and then up from A to A prime. All right, I'm getting a hand clap. -4, 1. So you can move left 4 and up 1, and notice that's true for all of these. Left 4, up 1. Left 4, up 1. So not bad at all, right? So I think you guys are gonna knock this out of the park. Ooh, do I have something a little bit more challenging for you yet? My Instagram. You never know. You never know when you're gonna need to. All right, example 4. All right, my friends, let's translate a figure. So it says translating a figure in the coordinate plane. Oh, you can translate things that are more than just triangles. We're gonna write this is called a rule for translation. And so let's see. I'm gonna just draw the points A, B, C, and D. So A is -1 up 2. A, -1 up 5. B, C is over 4 up 6. C and D is over 4 up 2. Ooh, I think I could make some claims about the figure. Oh, wait a minute. Yeah, that is 2. Okay. Yeah, it looks like 2 sides are parallel, 2 sides are not. So that would be what type of quadrilateral do you guys think? These look parallel. Looks like a trapezoid, my friends. Trapezoid. All right, and we want to plot it based off of this image, but we're going to move it using the transformation rule here, not using the graph. Okay, so let's see what happens, and we'll see if it lines up. So A prime, we'll write this out formally once, is going to be -1 plus 3, comma 2 minus 1. And so what I'm doing is I'm taking these original coordinates, I'm adding 3 to the x and -1 to the y. So A prime is going to be 2 comma 1. Not that challenging, right? So A prime is going to be over 2 up 1. A prime. Right. So let's see. So B prime. Let's have one of you guys help me out. B prime, -1, 5. What are the new coordinates for B prime going to be? Right, -1 plus 3 is 2, and 5 minus 1 is 4. I like it. Thank you, Emmett Math. No, okay. All right. But it's super easy. Okay. C was 4, 6, so C prime, 4 plus 3 is 7, and 6 minus 1 is 5. Right, so over 7 up 5. C prime, and then D prime, 4 plus 3 is 7 over 7, and 2 minus 1 is 1. And so you can get what was it? Yeah, 7-1. So you can get your points without a graph. I want to point that out. Here, don't pack up yet. We still got 5 minutes, friends. It's my 5 minutes. Mis amigos. All right, so and you can see that you could have described this transformation rule. We could have rewritten it as the vector 3, -1. There's just multiple ways of representing the same thing. The blue one is called the image. The green one is called the pre-image. Oh, yep. And then we did have that's what I thought. We got to talk about this. A rigid transformation, and this is a definition that's going to help us out for the rest of this chapter. Rigid motion is a transformation that preserves length and angle measure. Another name for a rigid transformation is an isometry. Iso, I believe, means equal, and metry means measure. Yeah. So a rigid motion maps lines to lines, rays to rays, and segments to segments. And guys, guess what? Here's a postulate for you to believe without proving. Let's see, just believe it's true. The old TP, a translation is a rigid motion. You don't have to prove it, it's a postulate. You just believe it in your heart enough. Like if it started to like wane in its popularity, if we all clapped enough, it would come back and like be as strong as it ever was. Also, there's this idea of composition of transformations, in which you can do multiple transformations one after another, and that's good stuff. The composition of two or more rigid motions is a rigid motion. That's a theorem, friends. Composition theorem. And basically that's saying, right, like if I map P, Q to P prime, Q prime, and then map that to P prime, Q prime, P double prime, Q double prime, the composition would be the shortcut. And that is also going to be congruent. All right, last problem. All right, good times. All right, graph RS. I can do that. Good. This time it's only a segment. -8 up 5, R. And -6, 8. So -6 up 8, S. There we go. And RS is going to be something like that. We're going to do a translation composition. Load disk space. What?